This video is for the Electrical Engineering 2FH3 course project. Our group number is B29 2018. We would like to extend our gratitude to Yam Shalich, our TA supervisor, for all the help he has given us throughout the project.
Hi, my name is Juan, and I will talk to you about antennas. Antennas are an essential component to radio communication and are used in all our day-to-day electronics for entertainment and wireless communication. Antennas are the interface between radio waves that are propagating through space and electric currents that move in the metal conductors contained in transmitters and receivers. So basically, an antenna is a transducer that converts radio frequency fields into alternating current or vice versa. Now there are two types. There's a receiving antenna or there's a transmission antenna. Now, antennas are crucial in the operation of all radio equipment, including wireless local area networks, mobile telephony, and satellite communication. Today we will be focusing on the horn antenna. The horn antenna, also known as the microwave horn, consists of a metal waveguide in the shape of a horn to direct radio waves in a beam. There are many types of horn antennas, including pyramidal, sectoral, and conical. For sectoral horn antennas, there are three different types. They are either E-flared, H-flared, or flared both in the E and H sections. Although in the market, dual flared sectoral horn antennas are most common. These horn antennas are typically fed by a section of a waveguide where the waveguide itself is fed with a short dipole. A waveguide is simply a hollow metal cavity, and these waveguides are used to guide electromagnetic energy from one place to another. In our case, the waveguide is a rectangular waveguide of width B and height A. I will now be talking to you about the physical structure of horn antennas. Antennas can be made from a variety of materials including aluminum, stainless steel, and more commonly, copper. However, the electrodynamic characteristics of a carbon composition antenna are being investigated and compared with characteristics of a metallic antenna with similar geometric parameters. It is found that the carbon composition antenna is practically identical to its metallic analog, but has superior mechanical parameters. The same way copper tubing carries water in our homes, it can also carry electrons in our antennas. One thing that makes copper an outstanding choice for antennas is that it is a very efficient conductor of electrical energy. In fact, about the only common element that is more conductive than copper is silver. You can imagine what an antenna built out of silver would cost. With copper being twice as conductive as aluminum and 6 times more conductive as steel, it makes an excellent choice as an antenna material. The increased electrical efficiency means more of your radio frequency energy will go up and out of the antenna and not be trapped, creating heat energy. More efficient radiation also means that you can run higher powers of the copper antenna than with other building materials. Also, the overall shape of the horn antenna can vary. As you can see from the picture, you can have a pyramidal antenna, you can have a rectangular horn antenna, both in the vertical direction or the horizontal direction, or you can have a conical antenna. These are all variations of the same horn antenna.
The antenna collects waves into the waveguide from the receiver or transmits radio waves from the transmitter through the waveguide out into space. In transmission, the radio transmitter supplies an oscillating electric current to the antenna, which radiates the energy as a moving transverse electromagnetic field wave. In reception, the oscillating electric and magnetic field of an incoming radio wave exert force on the electrons in the antenna elements, causing them to move back and forth, creating oscillating currents in the antenna, which are applied to the receiver to be amplified. The horn antenna resembles an acoustic horn. In acoustics, a waveguide is designed to provide an acoustic impedance match between a sound source and free air to maximize the efficiency with which sound waves are transferred between the source and the air or from the air to the receiver. In the same way, the horn antenna is considered to be a radio frequency transformer or impedance match between the waveguide feeder and free space. The horn antenna is a development of the waveguide transmission line. The waves of the signal propagate down the horn antenna toward the aperture. As they travel along the flared opening, the waves travel as spherical wavefronts, with their apex at the phase center of the horn. The spherical phase front along the horn antenna allows the phase to increase smoothly from the edges of the aperture plane to the center. Within a waveguide, several modes of propagation can occur, the most widely used being the transverse electric TE10 mode for rectangular waveguides. TE signifies that all electric fields are transverse to the direction of propagation and that no longitudinal electric field is present. Without a horn, a simple, open-ended waveguide is not very efficient. This is due to the fact that the sudden end of the conductive walls at the end of the waveguide causes an abrupt change in impedance at the aperture between the impedance of the waveguide and the impedance of free space. The sudden transition causes signals to be reflected back along the waveguide toward the source as standing waves. A significant fraction of energy is wasted, as not all of the power is radiated, which increases the SWR and can overheat the transmitter. The taper or flare of the waveguide changes the impedance gradually along its length, providing a gradual transition from the impedance of the waveguide to free space, acting like a progressive matching transformer. This allows more of the wave energy to radiate out the end of the horn into space with minimal reflection.
Hi, my name is Yusuf, and I'm gonna talk about the pros of horn antennas and its applications. So here are some reasons why horn antennas are very useful to the environment. One reason is that it can operate over a huge range of frequencies, ranging from 3.1 to 10.6 GHz. It also has a broad wide bandwidth and has a high gain because as the frequency increases, the wavelength decreases, and since the gain is inversely proportional to the wavelength in all horn antennas, the gain is very high. Finally, horn antennas have high directivity, which means that it can transmit and receive information over great distances. Horn antennas can be applied to many devices. One device that uses horn antennas are satellites. Horn antennas are used due to their high directivity to illuminate signals over large areas of the Earth. Horn antennas are also used as feeders in transmitting and receiving modes and for larger antenna structures such as parabolic antennas. They can also be used as directive antennas for devices such as automatic door openers or in microwave radiometers.
We chose a paper from the Journal for Progress in Electromagnetic Research. Our article was published in 2008 by Tadashi Hadari, Hassani, and Malahazde. The main adjustments made to the basic horn antenna was the introduction of a quadruple ridge waveguide with two coaxial probes inserted. They also continued the waveguide in order to match the horn antenna by flaring out the ridges near the transmitting end of the antenna. The group used coaxial probes in order to benefit the return loss performance of the antenna. The inner conductor of the coaxial probes passes through the first ridges and is then connected to the opposite ridges. The inner conductor and shield should enter very close to the edge of the ridges, as close as possible to the shorting plate, in order to maximize performance of the quadruple ridged horn antenna. As you can see from the figure on this slide, the group essentially continued the quadruple ridged waveguide with a bit of flare through the transmitting end of the antenna. Their goal was to maximize the antenna's attenuation at high frequencies. They've essentially added 10 different quadruple ridged waveguide sections, each of different height, which can be seen from the figure. After building a mathematical model of their proposed structure for the horn antenna, simulation results were carried out with two sets of industry-standard commercially available software. Computer simulation technology and high-frequency electromagnetic field software simulation was used. The figures in this slide show the electric field and the magnetic field at two different frequencies at the transmitting end of the horn antenna. As you can see, the attenuation of the signal, or the electric field lines, are basically similar within 8 gigahertz and 13 gigahertz. Simulation results were also consistent with both sets of software. The group also produces figures showing the magnitude of the electric field over two cross-sectional areas of the antenna at a standard frequency of 13 gigahertz. These are both acquired using the two different computer simulation methods talked about earlier. Our goal in our project is to reproduce the group's findings using OpenEMS, a MATLAB-based software that's open source. In order to do this, we have to reproduce the quadruple ridge waveguide with the coaxial probes into the common structure of the horn antenna.